He received the electronic engineering degree from Politecnico of Milano in 1992. Afterwards he joined STMicroelectronics and is now working on 3D graphics development and started 2D scalable graphics algorithms as well as architectural studies for set-top box and print clients. He's currently interested on computer vision and in particular on structure for motion, optical flow and visual search. He is a senior principal engineer, senior member of technical staff in STMicroelectronics and IEEE senior member. So welcome and above.
Thanks a lot for your kind introduction. The title of this contribution is Colored Noise Reduction for Embedded Devices. The authors of this paper are Valeria, Tomaselli, and Mirko Guarnera, belonging to Advanced System Technology, STMicroelectronics in Catania, Sicily. And the third author is Gregory Roffet from the Imaging Division of STMicroelectronics, Grenoble, France. Due to the fact that they couldn't attend by person, I presented the paper on their behalf. The agenda is as follows. We will introduce, I will introduce what's the meaning of the so-called color of chroma noise artifacts. Then we'll review quickly the state-of-art techniques against which the proposed technique, which is called the chroma washer, will be compared to, which is a method to reduce the chroma noise. Then test and comparison will be performed. Objective and subjective test will be performed, and finally we will go to conclusions and also future work in terms of potential enhancement of the technique. So what is the chroma noise artifacts? Is a very annoying artifacts affecting images which are taken in low light conditions. Usually they appear as quite large blobs, colored blobs, many pixels, and are in a region of a low spatial frequency. Here it is an example of this picture, especially focused on the background. But these artifacts is more pronounced on the darker regions versus the brighter one, and usually is more pronounced on the blue component rather than on the red one. The state-of-art techniques that are commonly used to mitigate this type of artifacts usually works in the luminance-chrominance space, like YCRCB or CIE lab. Usually median and average filters are used to achieve blurring effects in order to decrease these artifacts. However, this shows some consequences. For example, the color bleeding. Here you can appreciate the color bleeding, while on the next one there is no bleeding. So basically, located on the edges, the color tends to bleed through the region which are contiguous to these edges. And there is a further artifacts that is generated by using these techniques. Is that there is also a reduction on the saturation. Here another example with the saturation reduction, while it would be much preferable to not have the saturation reduction. So these are the artifacts used by large kernel, median, and average filters. One of the state-of-art techniques that we compared the proposed chroma washer was the DCT CNR. DCT is the discrete constant transform, which is well known and implemented in JPEG and MPEG encoder. CNR is the chroma noise reduction acronym. So this has been already presented back in 2010, And it is used as benchmark because its complexity makes it affordable on a mobile device, in particular on the JPEG encoders that are put right after the images. The method that apply is very simple to explain. Basically, every DCT coefficient is compared to a threshold, which is the Guarnera threshold, and depending on this comparison, the filtered sample is the difference between the DCT coefficients and the threshold, or otherwise is equal to 0. So as you can see, is exploiting the already existing and implemented functionality in order of the DCT within the JPEG encoder. And these are the results applying with these techniques. On the left we have the input, on the right we have the output generated by the DCT CNR. On the input, we added the Gaussian noise of sigma equal to 7, and basically these are results that are visible. So this is with the noise, and this is without the noise. So the method worked well, and perhaps there is also space for improvement. How? Thanks to the technique that has been proposed in the paper called the chroma washer. So, as we said, the chroma noise is characterized by large low frequencies colored blobs. Therefore, it would be natural to use large kernels, but large kernels, depending also on the size of the blobs, will imply an increase in hardware cost. Therefore, to mitigate this cost, it has been chosen let's say a first step, implemented the first step to downsample every component, so the luminance, the CRSB component. Then the denoiser was applied on the chrominance, then the upsampling was performed in order to have the denoiser chroma component. However, if a very aggressive subsampling is applied, the color bleeding will become more and more evident. Therefore, it is a compromise to subsample by 3 the image in every direction. And this is the compromise that we apply. Then also we introduce an estimation of a correction factor. In this case, we are interested to compute the dynamic in on all the planes, luminance and chrominance planes, in a 5 by 5 pixel patch. Basically, in this patch, we compute the difference between maximum and minimum, and we set 3 delta values, one for CR, CB, and one for luminance. Then, the correction factor is the dynamic of the luminance, if this is the minimum value between the 3 values. Otherwise, it's set to the maximum value of those 3 dynamics. Now, let's try to understand how this factor is applied. So, let's imagine that we are interested to apply this method on pixels around which there is an M by M pixel patch. So, I have the central pixel is the one we are interested to filter, and the pixel patch is M by M around it. Then the output of the filter is CR/CB, and it depends on the original value of the chroma plus a weighted difference between the denoised chroma and the original one. And the correction factor that I introduced before is feeding a function f, which is a Gaussian function, in this case as a sigma equal to 10, and basically for a higher value of the correction factor, the function goes to 0, and vice versa goes to 1. When it goes to 0, the output of the filter is simply the original value. While if it goes to 1, the weight of the denoised chroma increases. In the first case, so the color bleeding is minimized. So how to compute the denoise factors of the previous formula? This is a weighted sum over the pixel patch M by M. depending on the key azimuth value of chrominance within the pixel patch times a ratio between a weight, depending on the position, and their average within the pixel patch. The most important factors here are the weight at the numerator. In particular, these are exponential functions that depend on the difference between pixels within the patch. C is the central pixel, and K is one of the surrounding pixels within the pixel patch. And the strength of this coefficient can be also controlled through 3 sigma values, one for luminance, chrominance, CR, and CP. To avoid to implement in a costly way this function, lookup table can be a valid substitute. Now, the strength of correction, as I said, can be modulated thanks to sigma y, sigma CR, and sigma CB. And in this way, since consumer images tend to behave badly on the true components more than on the red components, it is possible to change the strength of the filter in order to mitigate more on the CB components rather than on the CR components. Let's go to the rules that are useful to define the die size of the denoising factor. As we said, the size of the pixel patch and by M influences the correction strengths. Therefore, its size is depending from the camera parameter, as we said. For example, to the exposure time. In particular, we implemented a functionality of the exposure time versus the window size, which is a piecewise constant approximation of a logarithmic function. So the higher is the exposure time, the higher is the size of the value, so the size of the pixel patch, in order to cope with larger colored blobs. Then we evaluated the algorithm in 2 ways, with objective test and visual assessment. Let's go to the first one. So, first of all, we start from a data set of images. Some of them are shown on the right part of the slide. We start from clean images. We add Gaussian noise with sigma equal to 30. We spread the blobs across the images in order to generate the colored blobs. Then we get the noise images. And then we mitigate the noise through the DCT CNR approach, and then we propose the chroma washer. Then we compute the signal-to-noise ratio, the peak signal-to-noise ratio between the output of the chroma washer and the clean images, the output of the blood filter and the clean images, and the output of the DCT CNR versus the clean images. And here are the results for different sequences, for different images versus the techniques. It is worth to notice that the minimum difference between the proposed approach and the DCT CNR is is close to an half of dB, while the difference between the DCT CNR output and the noisy is about 3 dB by average, while the proposed approach achieves more than 4.5 dB. Here are some examples of the images as a result of this processing. So on the top left, the original image. On the top right, the noisy one. So it is a principle the noise introduced. Then the output of the DCT CNR, still some noise is present. And the output of the chroma washer. By zooming on some details, you can notice that there are also blocking artifacts on the output of the DCT CNR due to the JPEG compression, while this artifact is not present at the output of the chroma washer. Moreover, there is no color bleeding, or is very, very mitigated, the color bleeding introduced by the chroma washer. Then we moved to visual assessment. Basically, we were interested to capture night scenes where the noise will be emphasized, because we are using 2 types of images embedded in camera phones at 5 megapixel resolution. So we got the noise images as captured by the sensor, then apply the chroma washer, and then perform visual assessment. So a small group of colleagues judged the images depending on the amount of reduction in terms of color noise, the color bleeding, the saturation, and the sharpness of the images. And here a couple of examples. So this is on the top left, the images as being captured, assumed version, the original, and the chroma washer. It is visible that there is a lot of chroma noise here, which is mitigated on the output of the chroma washer. And this is more evident by zooming on the picture. However, when we experimented on other images with the huge noise affecting the images, we were able, with the proposed technique, to reduce the color noise, while on the luminance, the noise was still evident. So what are the conclusions? With the chroma washer, it is possible to reduce efficiently colored blots that affect low light images without generating color bleeding or excessive reduction of the saturation. One distinctive point of this proposed work is that the behavior of the filter is influenced by the camera parameters like exposure time. And different type of strengths can be applied to the different component of the chrominance. So differentiating the behavior of the blue component and on the red component. And this makes suitable in hardware for embedded images, because also the memory has been limited thanks to the fact that the filter works in a downsampled version of the input images. However, still luminance noise is present, and so a future work to be performed is to mitigate also the noise on the luminance. Thanks for your attention. I may try to answer your questions, since I was not an author of the paper. You may kindly refer directly to the author, which are more than available to answer your question, and they told me to apologize for them not to be available to present.
Okay, thank you. Okay, are there questions from the audience?
So, for what I know, usually camera noise is box-on noise, not distortion noise. Have you ever also done some tests on that things? Because also for objective comparison here, just the author uses the distortion noise. So, like noise, there is some testing for some noise. What you can comment?
That's one of the questions I'm not able to answer. I think the authors tried by using real images, which are available in mobile phone, to capture the noise as it is. So I'm not sure that the authors experimented other type of noise other than Gaussian. However, on the other side, applied the method on the noise generated by real images. I'm sorry to not answer better than this.
Okay, is there another question? Seems not to be the case, and maybe I can ask a question. The algorithm highly relates on the down and up sampling. What algorithm is used for this? Do you know that?
I think, no, I'm not sure about what type of filter, but the constraints are quite significant. So I wouldn't imagine that the number of taps of the filter were huge, so few, I think. So it was an FIR filter. I think with minimized number of taps, honestly I don't know how many, and usually the coefficients are approximated as a shift in additions. So are not real numbers or fractional type of filter taps.
Yeah, because I was really wondering what the downsampling is doing to the noise. So I'm not really into denoising it, so it really would be interesting for me to know what is it changing the noise, or is it keeping the noise, or is it already denoising in some kind of way?
Well, as you may understand, depending on the type of filter and the response and frequency, usually they reduce the high frequencies. But since this is a low frequency type of noise, perhaps it doesn't affect too much the noise. On the other side, I think the real purpose for them was to decrease the complexity of the processing.
Okay. Oh, there's another question.
There is a tool named Neat Image. Do you know this tool? For denoising.
Say again?
Neat Image. Most of the best denoiser commercial tube compared to this tool. And maybe do you know how it works?
No, I'm not aware about it. So that's a good question. I will report to the outputs. How do you spell it? This?
Yeah, right.
Yeah, maybe you can do that afterwards. Okay, is there any other question? Okay, seems not to be the case, and thank you to the speaker again.